Welcome to Complex Analysis, Lesson 25 on Riemann surfaces. We'll start the discussion on the topic of branch points and then go on to talk about Riemann surfaces and give some examples. So we're going to talk about branch points first. Recall from earlier lecture when we defined the log of z, it was the natural log of the modulus of z plus I times the argument or the angle that z makes with the real axis, and then the value repeats every 2 pi I. That was the part that made the function multi-valued. So we can take the principal branch being between 0 and 2 pi, or you might recall we also said it was possible to go between pi and minus pi, or a number of other possibilities, but let's just take this as the principal branch. And what I want to show here is the concept of a branch point. So let's take on the left here we have, use the pointer, so on the left here we have a point z and we have theta, so that's the argument. And as we move around this closed path, you notice theta gets larger, 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 and eventually we get back to z, and theta is now theta plus 2 pi. So we get another value for the value of the log when we circle around the origin. And that's known as a branch point. Whenever you circle a point and you come back to a different value, the point is known as a branch point. Now on the right, let's just say we had another point here. Let me draw in, I don't know, just let's make believe that's a point. I know it's a little bit big, but let's say we have this point instead, and we go around that point from on a closed path. Then you notice the angle here, it starts out as theta, and then it gets a little bit bigger, then it starts getting smaller again, and then it grows a little bit, and then it eventually theta comes back to the same value. So this point I drew in here is not a branch point, because you can circle it and come back to the same value for your function in question here, log z. Now, of course, we can do branch points for different functions. I'm just using log z as an example here. So, in general, a point z is classified as a branch point of a multi-valued complex function, f of z, if the value of f of z does not return to its initial value when traversing a closed curve about z. So we saw that in the previous slides concerning our initial example, log z. There's some caveats to mention here. The closed curve is assumed to be sufficiently close to the point of interest. The behavior of paths that are some distance away from the point of interest are not relevant. So let's look at an example here. Let's say our f of z again is log z, and we have a point I, the imaginary number I, that we'd like to consider as being a possible branch point. So we take a closed path, to say this black one here, and in fact when you circle around, say starting from a point z sub 1, and you circle around and come back to it, theta does increase by 2 pi, and in turn the value of log of z1 when you return to that point is changed. So you might think that means that I is a branch point. But again, the condition here is that you need to be sufficiently close. So if we take a smaller closed curve, and in particular a closed curve that doesn't include the origin, then we see that and you take any point here, we see that if we follow the angle made between the point and the positive real axis, it does not increase to 2 pi. In fact, it gets a little bit bigger, it goes back to the initial value, then it grows a little bit, and then it's back to the initial angle again. So the log would be the same. It doesn't change. And since we have one counterexample uh, for our function log z in this case, then we say that the point I is not a branch point. In fact, if you pick any point other than the origin, you can always create a sufficiently closed curve where you would return to the same value. So we just have the one branch point for log z. We'll see some functions have more than one, but in this case we just have one. So what I just said is written here. If you're taking screen maps or you want to just pause the video and kind of reread what I just said, I'll leave that up here. So there's one other caveat which I'll mention at the bottom here. Further, it is assumed that there is some neighborhood of the branch point z where f of z is defined, albeit with multiple values, and that for any point z sub 0 close to but not equal to z, there exists a neighborhood around z sub 0 where f of z can be defined in a single valued and continuous manner. So for our example log z, we have the branch point at 0, and what this is saying is that, let me draw it here, it's saying that, so for any neighborhood about our branch point, and then any point, say that point there's some, we use another color, there's a neighborhood around that point where our function is single valued, and in fact that's true for log z and our branch point 0. So we have two regions here where log z is defined and single valued. So this first region is pretty obvious. We don't get anywhere near the branch point. The second region also avoids the branch point, and then recall we had stipulated the branch cut along the positive real axis, so we need to exclude that, otherwise we don't have a defined function. So let's continue on the next slide. We want to really determine the largest region where the log z is defined and single valued. What is the largest region for log z where it's single valued and defined? R2 from the region 2 from the previous slide gave us a hint. If we can just expand that and narrow it down so it covers or excludes just the origin and the positive real axis, then that would be the largest region where log z is single valued and well defined. We have other possibilities, which I've shown just a few here. There's an infinite number, but we can pick the branch cut to be the negative real axis, including the origin, and then everything excluding this ray here would be where log z is defined and single valued. Or we could pick the positive imaginary axis, or we could have strange curves going from the origin and continuous curves going from the origin out to infinity. Now this is, as far as I know, this is not used or anything like this is used. Normally it's just a ray from the origin, but just want to emphasize that you could have a branch cut like this. What's common in each case is you have the branch point is included in each case on the as part of the branch cut, and then everything other than the branch cut and the branch point are it consists of a region where the in this case the log z is single valued and well defined. So let's look at the function here, log z again, and imagine we have a z1 and a z2 just very close to each other, but on either side of the closed curve gamma. So as we start here with z1, the angle is almost 0, and as we go around the closed curve, the angle is almost 2 pi. So the value of the log at Z1 and Z2 is different on as close as you want to get to either side of the branch cut, which is a problem, right? We have this, no matter where we put the branch cut, we're going to have this type of situation here. So another way of, and this is where we finally get into the Riemann surface, another way of looking at this, trying to avoid the discontinuity, is to think of log z not as a function whose domain is defined in a plane, but rather on multiple levels or sheets, analogous to a multi-level spiral parking lot. So as we start out from z1 and follow the path gamma, as shown in the figure, and continue back to in the direction of z1, we end up not at the same point, but rather at a point above this. So we go all the way around. We're in the parking garage, for example, and then when we get here, we're going up, continuing up a ramp, and we're up. When we get back to Z1, we're kind of like one level above it in the parking garage, and that's known as a sheet. Now, of course, we could keep doing that. So as we went around a second time, we'd be up 2 levels, and then 3 levels, and so forth. And if we want the other way, we could go down levels. So basically, the discontinuity is avoided by having multiple sheets where you basically cross up another level each time you hit the branch cut. So these sheets are known as Riemann sheets, or the levels of the, analogous to the levels of a parking garage. They're known as Riemann sheets. Let's continue this discussion on the second slide. The infinite collection of sheets we describe for log z is known as the Riemann surface for log z. And I've shown a part of it here. These are the sheets, and of course there's an infinite number for log z, so it goes upward and downward infinitely many sheets. I took the figure from the Wikipedia article on Riemann surfaces, and I just used black and white. Other than that, it's the same figure. What's graphed here, an important part of when you graph Riemann surfaces is how you take this shortcut. Remember, when we're mapping complex functions, we're going from a complex plane, which is 2-dimensional, to the complex plane, which is 4-dimensional. So this is only 3 dimensions. The shortcut is we graph the coordinates in the domain. So we graph z, and then we graphed only the imaginary part. So that's the up and down thing here. So let's maybe just do that for a point. So if it's a point, what we're graphing is z, that's in the xy plane, and then in the up and down, we're only graphing the I argument z in this case here. And if we went up one level, then we would be graphing again z, and then it would be I argument z plus 2 pi I, since n is 1 going up. If we went clockwise this way, we went down a level, say roughly here, then this would, again, we would be graphing the z, the coordinates for z, and then just the I argument z minus 2 pi I. That would be this here. And keep in mind that the natural log of the modulus of z is the same. So you're not losing a lot of information here. Each one of these 3 points has the same real part in the codomain. It's just the imaginary part that changes. So that technique is used in general to graph Riemann surfaces. It's not just the convention I'm using here. We'll see that in a few more examples, some of which have just a finite number of sheets. It's also possible to just have a single sheet whenever you have, in fact, a single valued function, like the polynomials, complex polynomials, you're going to have a single sheet, and in which case the Riemann surfaces aren't that interesting in that case. It's also possible to consider the point of infinity as potentially being a branch point for a complex function. And the way we test for that is we use the, in this case here, the Greek letter z, xi, and we set that equal to 1 over the Roman letter 1 over z. And note that when the Greek letter z equals 0, the Roman letter z equals infinity. So it's easier to test for 0 here. So taking our example, we have log of z. We substitute in 1 over the Greek letter z, and that by using the property of logs, we get minus log of the Greek letter z. So since z equals 0 is a branch point of minus log Greek letter z, we know that the Roman z equals infinity is a branch point of log z. So we have a second branch point for our log, and then they're the only two actually, 0 and infinity. So we can do a branch cut, and what we would do here is we can view the branch cut as going from between the two branch points. One is at 0 and one is infinity. So we kind of saw that when we drew the picture, but now we can view the point of infinity as being sort of the other end point of the branch cut. We can do a slight variation of our example log z. Just take the log of z minus 2i, and in this case we would have the branch point would be 2i, and also the point at infinity. I didn't provide the details here, but it's the same analysis that we did for log z. So taking another example here, log of z squared plus 1, we can factor this to z minus I, z plus I, and then we know that the log of the product is the sum of the logs. And we want to analyze I and minus I as being potential branch points. So if we take a path around z equals I that doesn't include the other point here, z minus I, then log of z minus I, this term here, changes by multiples of 2 pi I when you return back to after following the closed path, but this does not return, this returns to the same value. So collectively these two added together, which equals this, our function f of z, does change by a multiple of 2 pi I whenever we circle a closed path about z equals I and return back to the same point. So that means that z equals I is a branch point. Then using the same argument, z minus I is a branch point. We can do the analysis at the point of infinity. We substituted 1 over z. We get this expression here. We just got to plug in the term here, then got a common denominator, and then use the properties of logs. So if we analyze Greek z equals 0, and not, so we take a closed curve about 0 but not plus or minus I, then this term here returns to its original value, but the minus log of z squared changes by multiples of 2 pi I, so this collectively changes by multiples of 2 pi I, which means that Greek z equals 0 is a branch point of this, which implies that Roman z equals infinity is a branch point of our original function. So we get a second branch point. So we have 3 branch points for our function here. Two valid cuts for our example log z squared plus 1 are shown on the left. We basically go from each branch point out to the other branch point at infinity, and both of these are valid. The one on the right is not, because we want to prevent um, a closed curve from encircling the branch points, and these two prevent us from doing that. We can't encircle the branch points with any closed curve, as you try as you may. But in this example here, we can fairly easily encircle two branch points if we use this cut, which is not, as I say, is not a valid branch cut. Three examples for you to try here. Find the branch points and possible branch cuts for these three functions. As a hint, you can use the properties of logs, or I would recommend that. So this first one is log z minus I plus the log of z plus the log of z minus 2i plus the log of z minus 3i. Work with that. And then the second one, you can be written as the log of 2 times z minus 1 plus 3 times log of z plus 3. The third one is a bit hard because you have an infinite number of branch points and they approach 0, and that could be a bit complicated in terms of the analysis. So finally, we'll do a function that's not log z. Let's take f of z equals z to the c, where c is a complex constant. We can write that in polar form, as we see here, then just expand it out. When a closed path about the origin is traversed once in the counterclockwise direction at a point z not equal to 0, is mapped by f of z to the point, and I just plugged in the 2 pi here for our argument. And you can expand that out like this here, just raising this to the c power. And then you notice this first part is our initial z to the c. So the effect of applying our function f of z to a point when we go around once counterclockwise is this here, this value here. And if c is not an integer, then we do come to a different value, which implies that that we have a branch point at z equals 0. Now, if c is an integer, then this e to the 2 pi I times an integer from Euler's equation is just 1, in which case we would return to the same value, in which case z equals 0 would not be a branch point. We could also check to see if z equals at infinity is a branch point. We use the same technique here. We put in 1 over the Greek letter z, and we get e to the minus c, which is basically the same form here. It's just a different, you can think of minus c as a different constant. And so z equals infinity is a branch point of our function z to the c. Again, that's assuming that c is not an integer. If a closed path about the origin is traversed n times in the counterclockwise direction, then a point z not equal to 0 is mapped by f to this point here. We were just plugging in 2n pi, because we're saying n here, n was just 1. Now we're going around n times. So we expand that out, and we get basically the original point, the original value, I should say, in the codomain, times this entity here, this expression here, e to the 2n pi ic. And if c equals m over n, where n is an integer, in other words, it's a rational number, then e to the 2n pi ic, the n cancels out, and you get e to the 2m pi I, which equals 1, which implies that z returns to its original value when a path about the origin is traversed n times. Continuing from the previous slide where we had c equals a rational m over n, if we start on the first Riemann sheet and go around the origin once, we reach the second Riemann sheet and the third until we arrive at the nth Riemann sheet. If we circle around once more, we come back to the original value, so we're on the first sheet again. So if f of z equals z to the m over n, where m over n is a rational number in lowest terms. So for example, if we had 3/6, we would write that as 1/2. So that has a corresponding Riemann surface of n sheets. So for example, z to the 1/2 has 2 sheets. Those are n equals 2. And z to the 1/3 has 3 sheets. Since n equals 3. As an example, you might want to think about z to the 2/3 or z to the 3/7. How many sheets do you have there? I'll talk about the graphs for these two on the next slide. So I have it written down what I'm going to say, but let's wait till I show you the figures. We can also look at f of z equals 1 over z to the m. We can write that as z to the minus m over 1, so our n equals 1 here, which means that we return back to the same value when we encircle a closed path about 0, which implies that we do not have a branch point at z equals 0. And if we put in z equals 1 over the Greek letter z, we get z to the m, and again that is not, we already analyzed, this is just a polynomial, so we don't have a branch point at Greek letter z equals 0, which means we don't have a branch point at Roman z equals infinity. And in fact, there are no branch points for this function here. The two examples we mentioned on the previous slide, z equals 1/2 and z equals 1/3 to the 1/3, are shown. The Riemann surfaces are shown here. I took these figures, changed them to black and white, but they come from the Wikipedia article entitled Riemann surface. Here you have 2 sheets. Here you have 3 sheets, as we mentioned. The reason for the intersection here is because we're drawing in 3 dimensions, we're drawing something that really properly exists in 4 dimensions, as I mentioned before. This is sort of a shortcut. In 4 dimensions, this is not an intersection. They actually do not the sheets don't intersect, and we avoid the discontinuity that we had with the branch cut. So there's no branch cut here. The main point of the Riemann surfaces is we avoid the branch cuts, and we just have these surfaces existing in 4 dimensions where the sheets do not intersect each other. Another example is f of z equals z minus some complex constant z sub 0 raised to the a power, where a is another complex number, times z minus z sub 1, where z is a constant, raised to a complex number here. From our previous analysis, we can conclude that z sub 0 is a branch point if and only if a is not an integer, and z sub 1 is a branch point if and only if b is not an integer, and the point at infinity is a branch point if and only if a plus b is not an integer. If a plus b is an integer, f of z returns to its original value after a path enclosing both z sub 0 and z sub 1. We need to justify what I stated in the previous slide concerning our example. We'll start by expressing z minus z sub 0 to the a power in terms of a polar coordinate system with origin at z sub 0. And you see here you have this vector from z sub 0 to z. It has radius r sub 0 and argument theta sub 0, and we're raising it to the a power, and we get this. And then we express z minus z sub 1 to the b power in terms of a coordinate system based at z sub 1. And this vector here raised is r1 e to the I theta sub 1, and then we raise it to the b power, and we get this here. All right, so it's a little bit unusual. I haven't done that in any of the other examples, but it facilitates the arguments, which we're going to talk about on the next slide. So let's continue with our example. We want to prove these three statements here. From the last slide, we showed that z minus z sub 0 to the a equals this expression in terms of the r sub 0 theta sub 0 coordinate system, and then we did the same for z minus z sub 1 to the b. We had this expression. So in terms of the two coordinate systems, we can multiply these together, and we get our original function f of z equals this expression here. If we go counterclockwise along a path that encircles z sub 0 but not z sub 1, the z minus z sub 0 to the a gets mapped to z minus z sub 0 to the a e to the 2 pi I a, but the z minus z sub 1 to the b just gets mapped to itself since we're not circling z sub 1. And in that case, if a is not an integer, then we have that z sub 0 is a branch point because the function comes back after circling z sub 0 on a closed path. It comes back to a different value. And similarly for z sub 1, if we encircle that and not include z sub 0, and b is not an integer, we come back to a different value. So z sub 1 is also a branch point. To analyze the point of infinity, when we encircle the point of infinity, we in fact encircle both z sub 0 and z sub 1, encircle the whole plane really, and so the function gets mapped to what's shown here. The important part is the a plus b. So if a plus b is not an integer, then we know from our analysis of the z to the z example a few slides back that this is a different value. It's not equal to 1, and that implies that z equals 0 as a branch point. So that's it for this lesson, and unless I get further comments or suggestions, I think this is probably the last lesson in my complex analysis series. So thanks for listening, and feel free to make comments or suggestions, and if you like the video, please give it a thumbs up. Thank you.